Well, you see my title here, The Joy of Research in Fluid Dynamics. And you see a picture of a wonderful vortex ring that was observed, emitted by the eruption of Mount Etna, the volcano in Sicily, in the year 2000. A wonderful picture that was taken. The actual volcano is way down here off the screen. This is the sun shining through the cloud. It's actually a steam ring, as it's described, rather than a smoke ring, but it's the same principle. It's a vortex ring that's carrying the steam along with it, and it's a highly turbulent and highly complex flow, so very appropriate for a meeting on complex motion in fluids. Well, we were both 26 at that time, and anyway, as I say, it was a great achievement for Linty and a great distraction for me. And I presented some of my thesis work at the famous 1961 Marseille Symposium on Turbulence. And you see the amazing people that were among the participants of that. The Russian group, Kolmogorov, Abukov, Yaglom, and Milyonchikov. Theodore von Karman was there, and G.I. Taylor, and they greeted each other warmly every morning and brought, whoever was lecturing, brought to a standstill, because von Karman had the habit of coming in a little bit late. He would come down the aisle and shake hands with everybody. The poor lecturer. And he would end by greeting G.I. Taylor, a warm embrace in the front row. Well, that was a terrific meeting, as you see. You see the names. These were young men in those days. Stan Corson, Philip Safman, Les Cavazny, Bob Craiknan, John Lumley, Ed Spiegel. They're all such well-known names in the field. And, of course, George Batchelor himself, who was the moving force behind this meeting. This is the volume of proceedings, Mécanique de la Turbulence. And this was the abstract of my paper, which is so small I'm glad you can't read it. But you see that I was thrown in very much at the deep end. And my moral, there'll be a number of morals for you in this lecture. My first moral is be sure to choose a brilliant research supervisor. And that was George Batchelor in my case. Here now is the first experiment conducted in that laboratory at Eulers' disk. And I regard this as a prototypical example of a finite time singularity, which I'll show you in this little movie. And I think we're linked up to the audio. So it's going to be a little noisy, but that's quite deliberate. So let's see if I can... You see, it's noisy even before it starts. And I'll advance this a little bit. I'm just... You can even hear me whispering. Many of you may have seen this phenomenon before. A rotating disk, that's all it is. It's actually rotating on its rim. It's precessing rather rapidly. You see the frequency is increasing. Well, that is a finite time singularity. There's no question about it. We're all very interested in the phenomenon, the possible existence of finite time singularities in fluid mechanics. And this is really why this phenomenon attracted my attention. And the immediate question is how actually, well, one question, there may be many others. You see, if you consider that problem as a problem in ideal analytical dynamics with no dissipation, then it will precess like that forever. Forever. I think Euler knew that. I can't find it anywhere in his writings, but I'm pretty sure he could solve that problem. But as soon as you have a little dissipation, the whole thing changes. Firstly, it seems to precess more and more rapidly, which is strange for a start. The note, the sound, the frequency goes up. And secondly, you have this finite time singularity, so utterly different from the ideal situation. And that's caused by dissipation. Something is dissipating the energy. And the question is what? Well, I naturally, being a fluid dynamicist, I thought the thin film of air between the disk and the substrate being jiggled back and forward very rapidly is dissipating energy by viscosity. Admittedly very weak viscosity because it's air, but still, what else? However, that's extremely controversial. That was my answer at the time in the year, I think it was 1999, hotly disputed. The alternative that's put forward is solid rolling friction. A slight deformation at the point. It's not really a point of contact. It's a little area of contact. So it becomes a very, very difficult problem, I think, in solid mechanics. Anyway, that is the Euler disk, and I have the real thing over there, which we could play with later if you.
This is a Celt stone, found in archaeological sites all over the world. Archaeologists became intrigued with these when someone happened to spin one on a table, and they found that it would stop spinning, wiggle a bit, and then spin in the opposite direction it started with. Also, if you just push down vertically on one side of the stone to make it rock back and forth, it will suddenly start spinning around. Now, these stones were typically used for axe purposes, but today we have a different name for something that has the shape that can make it reverse its own spin. It's called a rattleback. Let me show you how they work. The harder I try to spin it, the harder it goes back the other direction. Like, look how much momentum I'm giving this, and it just stops and then goes the other way, completely reversing the angular momentum. So how does something completely reverse its angular momentum and spin the other direction? Well, there are three components that make a good rattleback. The first one is that the elliptical bottom of the rattleback doesn't align with the top. So if the top were a rectangle, the elliptical bottom would be offset a bit. Also, the radius of curvature of one side of the ellipsoid needs to be different than the other side, kind of like a spoon or an egg shape. And finally, the mass distribution needs to be different for both sides of the principal axes. It has to be able to wiggle a bit from being off center and rock back and forth. With these components in place, you now have a good rattleback. Notice how I can push it straight down, but it becomes unstable and then starts to spin. Or if I spin it clockwise, it will spin and then stop and wiggle a bit and then spin the other direction. In fact, if I just set it down on a vertically vibrating plate, it'll spin counterclockwise indefinitely, as long as this plate keeps vibrating. The rattleback will just keep spinning. For example, I have a freezing cold aluminum block that I'm going to pour some water on to make a thin sheet of ice on it with low friction. Watch what happens when I spin it on it now. It can't reverse. But if you have too much friction, then the spinning stops before it can rock unstable enough to reverse the spin.